Expression for maximum work in reversible and isothermal process. Now consider n moles of an ideal gas enclosed in a cylinder which is fitted with a movable rigid piston. It expands isothermally and reversibly from initial volume V1 to final volume V2 at temperature T. So this is the piston which is kept here. So this gas expands reversibly and isothermally, means at constant temperature. So as I explained in the earlier videos also, reversibly it can be expanded if you put some weights over here, and if you are removing a small weight or small mass from here at a time, there will be very small change in the volume which can be denoted as dV. So this reversible process, it occurs in number of steps, and that is why this can be reversed at any step, and maximum work is obtained in this reversible reaction. Now when the volume of gas increase by infinitesimal amount dV, infinitesimal means in very small amount, that is in dV, in single step the small quantity of work is done. It means that when there is a very small change in the volume, or whether there is an increase in the volume by a very small amount, that is dV, in a single step, naturally the work done obtained will be again a very small, which can be denoted by dW equal to minus P external into dV. Okay, so as the expansion is reversible, as we are saying that the expression for maximum work in reversible reaction, so as the expansion is reversible, P is greater than the very small quantity, that is dP, than external pressure. So what is this P? P is the pressure of the gas. So P is the pressure of gas, which is very small, which is greater by a very small quantity, that is dP, by the external pressure, that is P external, that is the external pressure which is applicable on the gas. So as this change or these values of P and P external differ by a very small amount or infinitesimal small amount, that is dP, so we will get here P minus P external is equal to dP, or we can write here, we can further write P external will be equal to P minus dP. So you number this as equation number 1, we number this as equation number 2 here. Now when you combine these two equations, on combination of these two equations, you will get here, you can write further dW is equal to minus P minus dP into dV, means we are substituting here value of P external. P external equals to P minus dP. So dW is equal to minus P minus dP into dV. We are getting here the next equation here on combination of equation number 1 and 2 here. Now if you further proceed for the equation, like if you further simplify this, you will get here this dW is equal to minus P dV plus dP into dV. I'll write here again the equation, dW is equal to minus P minus dP into dV. Okay, so this P minus dP into dV, so this dV is to be multiplied by this bracket, so minus P into dV plus dP into dV. Okay, so here this is the small changes in pressure and the volume. So you can neglect these two terms. You can neglect this, because if you multiply a very small value by again a very small value, will be getting very small thing. Means 0.1 into 0.1, you are getting here 0.01. So you can naturally neglect this dp into dv. So neglecting the product of this dp and dv, which is very small, you will get here dw is equal to minus pdv. So this will be your equation number 3. Okay, the total amount of work done during entire expansion of from volume V1 to V2 would be the sum of infinitesimal contributions of all the steps. Means if you again come back to this gas is expanding in very small steps. So if you combine this whole here from initial, this is the V1 and it can reach up to this volume, and during this expansion it undergoes very small steps. So if you combine all these steps, that will give you the maximum work done. So you can further write here like dw, that is, you have this equation dw is equal to minus pdv. Now the total work is obtained by integrating this equation number 3 between the limits of initial and final state. This is the maximum work. As the expansion being reversible, so we get here, we integrate this, we combine all these steps together, you will get here between the limits initial and final. So you will get here dw is equal to minus integrating between the limits v1 and v2 pdv. So w max will be equal to here minus integration v1 to v2 pdv. So this is your equation number 4. Next will be using this ideal gas equation. You know this ideal gas equation. You can write here ideal gas equation as PV is equal to nRT, or we rearrange this, P is equal to nRT upon V. So this is applicable. We are considering a gas, so we take into account the ideal gas equation and apply this ideal gas equation to this equation number 4. So you will get the next thing, that is W is equal to W max will be equal to minus integrating between the limits nRT dV upon V. We are just substituting the values here. So you can write further minus nRT. These are the constant things. You can keep this outside this integration sign and integrate this between the limits V1, V2. It will be dV upon V, where this T is taken as constant. Okay. Now further you can write minus nRT, that is log to the base E, that is ln V, V1 to V2. So derivative of log V is 1 by V. So integration of 1 by V will be equal to log V. You know this thing. So you can further write in the next step minus nRT. You simplify this, that is ln V2 minus ln V1. Next step you can write minus nRT ln V2 upon V1. Okay. Now the next would be W max equal to, now replace this or remove this ln by log to the base 10. You will have to multiply this by 2.303 nRT log to the base 10 V2 upon V1. So this is the next equation that you will be getting. That is equation number 5 here. Now at constant temperature, P1 V1 will be equal to P2 V2. Now if you rearrange this equation, that is P1 V1 equal to P2 V2, if you rearrange this equation, you will get V2 upon V1 will be equal to P1 upon P2, isn't it? Now replace this V2 by V1 in equation 5. We will get the final equation, that will be W max equals to minus 2.303 nRT log to the base 10 P1 upon P2. So this is your equation number 6. Now you can solve the problem based on either this equation if pressure is given, and you can solve the equation by using the equation 5 if the volume is given. Thank you.